important that you become familiar with these units of measurement for your future work with capacitors. Let's look at the second important device, inductors.
Like capacitors, inductors are widely used in electronic systems. Inductors come in many shapes and sizes. They are sometimes referred to as coils or chokes.
But regardless of the descriptive term used, an inductor is simply a length of conductive wire that is wound into a coil. Let's examine an inductor's basic operation.
In the previous discussion, you saw how a capacitor stores an electrical energy in the dielectric. An inductor also stores electrical energy, but in a different way. Remember that when current travels through a conductor, an electromagnetic field forms around it. It is within the field that an inductor stores electrical energy. This property is called self-inductance, but is usually referred to as simply inductance. The symbol for inductance is a capital letter L.
Let's examine how an inductor works using this DC circuit. When current flows, a magnetic field is established around the coil. An increase in current expands the field, while a decrease in current reduces the field. In other words, a changing current produces a changing electromagnetic field around the inductor. This changing magnetic field, in turn, induces a voltage across the coil. The polarity of this induced voltage is such that it opposes changes in the magnitude of the current. This self-induced voltage created is referred to as a counter-electromotive force, or CEMF. It's important to realize that the magnetic field will only change while the current is changing. Once the value of the current is established in the DC circuit, the CEMF will stop being induced, and the inductor will behave as a resistor, equal to the resistance of the wire out of which the inductor is made.
Although the explanation so far has involved the DC circuit, the operation of inductors relies on the fact that there is a varying voltage or current present as found in AC. Let's take a closer look.
During the first quarter cycle, the increasing voltage of the AC source produces an expanding electromagnetic field around the coil. This, in turn, induces a voltage within the coil of the same magnitude as the source voltage. Current flows through the circuit in the direction shown. During this first quarter cycle, the inductor is drawing energy from the source. During the second quarter cycle, the source voltage drops off. As this happens, the magnetic field around the inductor collapses, inducing a counter-EMF and returning energy to the circuit. The current flows in the direction shown. Between 180 and 270 degrees, this same process is repeated, but with opposite polarities. The increasingly negative source voltage results in an induced counter-EMF whose polarity opposes the increase in current. This is because it takes time for the inductor to build up its magnetic field. But once again, during the final quarter cycle, the magnetic field collapses, inducing a CEMF which will oppose the change in current. The inductor returns energy to the circuit to accomplish this. To summarize, the inductor alternately draws energy from the source and then returns the energy that has been stored in its electromagnetic field back to the source twice each cycle of AC. Since the net energy drawn is zero, the power consumed by the inductor in this circuit is zero.
Just as capacitors can have different types of dielectrics, inductors can have different types of cores. Don't forget that the strength of a magnetic field depends on the type of core material used.
The type inductor symbolized on the schematic so far has been for an air core inductor. Some applications require an iron core inductor, which is schematically represented by a coil symbol with two lines next to it indicating the presence of an iron core. The schematic symbol for a variable inductor has an arrow through it. This type has a movable metal core. The base unit of measurement for inductance is the Henry, abbreviated with a capital H. An inductance of 5 henries would be written L equals 5H. The Henry is a large unit of measurement. For many practical applications, 2 smaller units are employed. One is the millihenry, abbreviated with a lowercase m and a capital H. A millihenry equals 1,000th of a henry. The other is the microhenry, abbreviated mu, capital H. A microhenry is equal to 1/1,000,000th of a henry.
Stop the program and complete activity number 3. When finished, continue watching the program.